coefficient. Record the data for the steps below on the second page. Right here, this is where they go. Use the fractional height at parachute deployment and the actual height to find the actual height of the parachute at deployment. Fractional height at parachute deployment and the actual height at apogee. Okay. So here is the actual height at apogee. I cheated a little bit. I got ahead of the game. I went to this sheet and I found that 56.25. So let's enter that as 56.3. Now that's the apogee. We want the parachute deployment. We found earlier this fraction. This is 0.839 is the ratio of the deployment height to the apogee. So if I multiply that ratio times the apogee, that should give me the deployment height. I can just do it in here. This times this will give me 84% of 56.3. So there. That's when the parachute deployed. The descent time we can figure out up here because we've got the time that the rocket touches the ground and then the time when the parachute deployed. So this is descent time while the parachute's deployed. It's just going to be this minus this. Terminal velocity with the parachute. So we're assuming, I want you to assume, that when the parachute's fully deployed, it comes to terminal velocity really quickly and then stays there. So it's at terminal velocity for this whole 30.7 seconds. Terminal velocity means there's no acceleration, it's constant velocity. So we could just use distance equals rate times time. The time is 30.7 seconds. The distance is 47 meters. So the velocity is going to be distance over time. Well, not exactly. The speed is distance over time. That's the terminal speed. To make this velocity, let's put a negative in there. All right. Estimated radius of the parachute. My parachute was about 0.8 meters in diameter, so it was about 0.4 meters in radius. Cross-sectional area, the area of a circle with that radius, is pi r squared. Here's how you do pi in a spreadsheet. Pi and open and close parentheses times radius squared. So about half a square meter. The drag coefficient, got to use the drag formula and weight again. So at terminal velocity, weight and drag are equal. So weight is mg, drag is 0.5 times cross-sectional area times drag coefficient times density of air times velocity squared. So I'm looking for the drag coefficient. So basically I'm going to keep that mg from one side of the equation and I'll divide it by everything except drag coefficient from the other side, therefore isolating drag coefficient. So mg is the weight. I'm just going to look in my other spreadsheet. The weight is 1.96. I'm just going to put in 1.96 instead of negative 1.96. 1.96, that's the weight, divided by, and then this is where there are all these things multiplied together. The cross-sectional area times the, let's see, density of air, 1.21, times, by the way, if you copy from that other spreadsheet and try to paste here, it doesn't work well unless you do a trick. So I'm just typing in the numbers. Times, and then velocity squared. So this squared. 1.36, that's a good parachute. Apparently, really good parachutes have a drag coefficient of 1.5, maybe even higher.